Good evening to the Madison DX Club's June 2026 program, and I'd like to turn it over to our
Here is the
program
direction you're
chairman
looking for.
to introduce tonight's speaker. Bob?
Yeah, so we have a really interesting program tonight. Frank Donovan is with us. Frank is well known for his accomplishments as a DXer and a contester, and I think he's been quite active in supporting radio clubs, and he's also done a lot of work in propagation. So that's what we're going to hear about tonight. And really looking forward to this, Frank. And thanks so much for joining us tonight and doing this for us.
Okay, Bob, thank you very much for the introduction. So let me get my slides here and see if we can get underway. You should see my full screen slides now.
Nope.
No, I haven't. Okay, so I need to share my screen. Let's see, where is this share? Right there. You see my screen now?
Yes, yes,
And now you should see my slides.
yes.
Okay, great. Let me get this thing out of the way. Okay, well, this is a particularly interesting time for this presentation. I do a propagation forecast 3 days a week in the Daily DX. Some of you may see it. And this is one of those weeks where the forecast, which I derived from a lot of professional sources, was completely wrong. And that happens. Part of my professional career was involved in technology forecasting. And if there's one thing you learn when you do forecasting, is you learn to be humble. Because you're going to make mistakes. No matter how reliable the source material is that they use, the universe doesn't subscribe to the Daily DX and didn't behave the way we expected for the last few days. So that was good because the forecast was for some pretty terrible geomagnetic storms for the last couple of days, and they didn't materialize, which is wonderful for us DXers and contesters. So it's nice when we get surprised in a good way, and that was in a really good way. Okay, so this is a very complex topic, and we're just going to scratch the surface. These are 3 publications that I highly recommend for people who are interested in learning more about this fascinating aspect of our hobby. The one on the right side, radio wave propagation, is very basic. It's written for everyday hams. It's very readable, and it's not terribly expensive. And I always recommend this as a first book to acquire and learn about propagation and how it affects our ham radio hobby. It's very readable. The other 2 books are really reference books. They're very excellent. Both of them are written by hams like myself, for hams. Most of us have professional backgrounds, so our knowledge is quite extensive, and we try to capture useful parts of that for the ham community. The propagation aspect is covered in detail in the ARRL handbook. The propagation chapter was completely written by myself and others for the 100th edition handbook, and the current handbook propagation chapter, to the best of my knowledge, is unchanged. And the antenna handbook doesn't really get into propagation very much, but one of the reasons we study propagation is so that we can improve our antennas for the various circumstances we encounter. It's hard to design really effective antennas without understanding the nature of propagation and how it is that you direct your signal to take advantage of that. Especially height above ground is a very, very important consideration. Okay. I'll just mention a couple of things before I get into the presentation about the style. of my presentations. It's a little different than probably a lot of the ones you've seen. The slides that you're going to see are very detailed and they're very readable. I do not read my slides, and you shouldn't feel that it's essential for you to read them as I go along either. The best thing to do is to listen to what I've got to say. You can always go back and look at the presentation again later, and the slides themselves will be available for you to download, and you can read them in detail later. So the more important thing to do is to listen and try to get what you can out of the slides, but don't expect me to read them because I won't do it. But I will cover some of the most important points. If I tried to read these slides, we would be here for the rest of the night. Importantly, all aspects of radio propagation derive from the sun's magnetic field. And the sun's magnetic field is extremely variable and very hard to forecast, as we discovered for the last few days. The forecast was for some moderate to severe geomagnetic storms, and they just didn't materialize. So these are some of the important aspects of propagation and some of the topics we'll cover today. The sun's magnetic field is central to everything about HF radio propagation. You can argue that if the sun didn't have a magnetic field, that we wouldn't exist on the Earth. Active regions, these used to be called, for some of the older hams like myself, these used to be called sunspot groups or sunspot regions. And what was discovered as the study of the science of the sun is that these sunspot groups include not only sunspots, but very importantly, some of the most significant disturbances to propagation also originate from the active regions or very close to them. And primary among those are coronal mass ejections, abbreviated CMEs here, and solar flares. And we'll talk about all of those three topics in the course of the presentation. The beneficial radiation from the sun is from a type of radiation known as extreme ultraviolet radiation. That refers to the wavelength of the ultraviolet radiation. So we all know about UV from going to the beach and protecting ourselves from sunburn, and the ultraviolet radiation is at a slightly different wavelength than the UV that gets through the atmosphere and down to our favorite beachfront location in the summer. Almost all strong geomagnetic storms are caused by coronal mass ejections. These are extremely powerful ejections, millions of tons of solar matter molecules ejected from the sun and following the interplanetary magnetic field. That's the sun's magnetic field extended into space. And eventually our little tiny planet called the Earth encounters these ejections of billions of tons of solar material and causes these huge storms. We'll talk about that and what effects they have. And we were expecting those this week. Thankfully, they didn't happen. There's also very importantly something called the solar wind. This is the predominant cause of disturbances during the declining phase of the solar cycle, like we are in right now, and especially during solar minimum when CMEs become very infrequent. And the high-speed solar wind, deriving from these coronal holes, is the cause of most minor geomagnetic storms, especially during solar minimum when the really severe geomagnetic storms become uncommon. Also, so we talked about the sun's magnetic field. It extends throughout the solar system to well beyond the Earth. And it's called in that space, it's called the interplanetary magnetic field, but it's still the magnetic field of the sun, extending out countless tens of millions, hundreds of millions of miles and more, all the way to the edge of the solar system. It gets weaker as you go along. The sun's magnetic field is extremely intense on or near the visible surface of the sun, and it's still somewhat strong as it gets to the Earth's orbit. But thankfully, the Earth's magnetic field is much stronger, and that protects us from most of the effects of the solar magnetic field, the IMF. We'll talk about the importance of the orientation of the interplanetary magnetic field. You probably recall from elementary school that all magnets have a north and a south pole, and so does the sun's interplanetary magnetic field. And the orientation of that field when the Earth crosses it has a big effect on geomagnetic storms. And the last big topic, we'll discuss solar flares, which are pretty remarkable when you experience one. And I'm sure some of the people attending this meeting have experienced solar flares. And I'd encourage you when we get to that point of the presentation, if some of you have experienced this, if you could just try to unmute your microphone or notify the moderator, and we'll see if we can get some of your comments either during the presentation or afterwards. It'd be interesting to learn of some of your experiences. They're quite dramatic, the long-lasting, strong solar flares. So we're in the declining phase of solar cycle 25. We're probably right on the border of the end of solar maximum and the beginning of the declining phase. The solar cycle is often referred to as 4 phases. So they're not individual points in time. Like, a lot of people are interested in, when exactly did solar maximum occur? Well, it was around September of 2024. But most importantly is, how long did the solar maximum phase last? When did it begin? When did it end? And what's next? Well, the answer to those questions are that the solar maximum phase began about the end of 2024, and reached a maximum. I got that date wrong. It's in the presentation a little bit later. So it began about 18 months before solar maximum. Solar maximum was around September of 2024. And now here we are at the end of 2020, nearing the middle of 2026. Next month, well, later this month will be the middle of the year, and we're just about at the point of ending the solar maximum phase and beginning the decline, where a lot of these dynamic characteristics, mainly of disturbed conditions, become kind of the prominent feature of radio propagation. And what happened this week with that expected geomagnetic storm that didn't occur is a classic of the dynamics and unpredictability of a lot of these events. And also, very importantly, from a propagation point of view, and anybody who's been a ham for a while is well aware of this, and that is there's a very big seasonal component to the variability of HF radio propagation. It's quite remarkable. So the 2 major DX contests ever since the end of World War II have been the CQ Worldwide DX contest in October, November each year, and the ARRL DX contest, which used to be a total of 4 weekends, in February and March of each year. And it's quite remarkable because the hams that chose those dates were very aware of the variability of solar disturbances, and they selected those dates to have the least likelihood, to have the best likelihood of high MUFs with an acceptable amount of geomagnetic disturbance. It's quite remarkable that they picked, what are arguably the two very best times of year, and probably October and late February, early March are the two very best times of year, and we enjoy those DX contests a lot to this day because they selected exactly the right time of year to have those contests. So I mentioned the four phases of the solar cycle that are illustrated here. Solar maximum was around September of 2024. And I was trying to remember the date. The transition into solar maximum began in December of 2022. We reached the maximum a little more than just a little less than 2 years later. And then we are just about on the edge right here of the end of the solar maximum phase and entering the declining phase. And the declining phase is characterized by lots of disturbed days and a lot of dynamics. So coronal holes, anybody who reads my propagation forecast, I sometimes refer to these. This is an image of a coronal hole on the surface, on the visible surface of the sun. The sun is a gas star. It's not solid at all. What you're observing here is a visible feature on the surface of the sun, the visible surface. And it's huge. It's one of the most massive things in the solar system. This particular coronal hole extends all the way from the most northern regions of the solar surface, all the way down to the sun's equatorial region, and then halfway down to the South Pole. It's huge. What's important about these is their orientation with respect to the Earth. And the area that's of most significance in terms of affecting HF radio propagation is when these coronal holes are aimed directly at the Earth. So sort of, if you look at the kind of the center 20 or 30% of the sun, when the coronal hole is there, so it's kind of pointed right at the Earth right here, that's when the effect is greatest. It takes about 2 days for the material from emanating from the solar wind to make its way to the Earth. So visually, we can see this coronal hole here, but the material being expelled from the sun, lots and lots and lots of, I'll just call it sun stuff, highly charged particles and their associated magnetic field. About 2 days after this image was taken is when all of that stuff appears in the Earth's outer atmosphere, specifically the ionosphere and an area known as the magnetosphere. So with all that as background, let's take a look at where we are. This particular slide is, it's about 4 months old now. It's updated every month by the NASA Marshall Space Flight Center on their website, shown here. You don't have to write that down because you'll have access to these slides later. And they produce their forecast of solar cycle 25 in kind of an interesting way. And the black line shown here shows a solar maximum, which occurred in about September of 2024. And then the 4 colored lines are 4 alternative forecasts. So instead of producing just a single forecast, they produce 4 of them and describe them in terms of the most likely in a beneficial way, most likely in terms of a 50-50 probability, and the least likely forecast. It's still a legitimate forecast, but pretty unlikely. So the forecast that we're primarily interested in is the 50th percentile forecast. So it's about 50-50 chance of being right, or a little too optimistic or a little too pessimistic. and the 75% one, particularly if you tend to be an optimistic kind of person. The one shown in blue is unreasonably optimistic. It's the 95th percentile one. You wouldn't go to Las Vegas and gamble this way, I don't think. And the least likely one is in red. That's the 5% one, which means that the actual solar cycle will exceed these numbers 95% of the time. So it's the middle ones here. So what's significant about that? On the left side, these graphs are showing solar flux units, commonly just called the solar flux. You've probably seen that in propagation forecasts, versus time. And the two especially significant things about that, you'll notice during solar maximum, from about the middle of 2023 through about a year ago, when the solar flux was around 160 or above during most days. During that period, for those of you who were active last year or the year before, 10 meters was open almost every day from September through April or May. You could turn the radio on, and almost every day you could expect 10 meters to be open all over the world. This was really a pretty good solar cycle. Well, we're now at a point in the solar cycle where we're down around here, where most days, instead of having solar flux around 160 or even 200, we're having solar flux numbers varying from about 100 to maybe 130, 140, occasionally higher. So we're down here. And what's happening there is that 10 meters is not as reliable as it was a year ago or 2 years ago. But we've got a long way to go down this forecast. So once we cross the threshold of about solar flux 100 is when 10 meters becomes pretty unreliable. If you're a serious 10-meter DXer, you can still work lots of stuff on 10 meters, even when the solar flux is below 100, but you really have to be eagle-eyed to really pay attention to what's going on 10 meters. Whereas a year ago, all you had to do was turn the radio on, and the band was going to be open, but down here, you have to spend some time. And we'll give you some hints about how to do that more efficiently. I'm going to skip through all these individual. Okay, so the primary region of interest in the ionosphere is known as the F2 region. We used to call that the F2 layer, but scientists said, look, these layers are very wide, and it's really not appropriate to call them layers. They're really regions of the ionosphere. They extend from about 250 to about 400 kilometers above the Earth's surface, and the height above ground varies between day and night. So they're referred to as regions now, the F2 region. We'll talk about two other especially important regions, the E region and the D region. But from the point of view of DXers, what we really, really care about is the F2 region, because it's so high above the ground that it gives us 4,000 miles of coverage. I'm sorry, 2,500 miles. 4,000 kilometers of coverage in a single hop. And in two hops, we can go 5,000 miles. And there's a type of propagation we'll talk about called long path propagation that allows us to use the F2 region to propagate more than halfway around the world. And some of us, I certainly have experienced this a few times, have heard our round the world echoes, which takes a little less than a quarter of a second. So it's really obvious when it's happening. The F1 region is a less important region. The F region splits into the F1 region and F2 region, especially at lower latitudes and especially during the summer. Mostly the F1 region does not work to our benefit. It's much lower above the Earth's surface. So if we happen to propagate, if the F region happens to be present and our signals bounce off of the F1 region instead of the F2 region, they cover shorter distances because it's not as high above the ground. So we like to to operate on frequencies in which the F1 region is not important. So generally, if we operate on the highest band that is open, we can avoid the undesired result of having our signal, as is shown in this red, reflect off the F1 region instead of the very high F2 region. F1 region is not present at night. It's a daytime phenomenon that complicates propagation, especially in the 20-meter ham band and especially at lower latitudes, like down in the Caribbean. There's a huge seasonal variability. So we talked about all of this solar-related stuff, and then reminded everyone that the Earth has seasons. The Earth's rotational axis is tilted 23.5 degrees, and we have seasons, and we also have propagation seasons. One of the things that happens that can be quite a problem, especially during the summer, and especially down in the Caribbean or down near the equator, down in Brazil, for example, is that the E region becomes so heavily ionized in the summer that our signals, instead of propagating upwards to the ionosphere and we go all the way up to the F2 region, 300 to 400 kilometers above the Earth, and then coming down, instead our signals get up to the E region, and it's so well ionized in the summer that our signal bounces off of the E region instead and doesn't get up to the F2 region. Anybody that's operated field day, for example, on 20 meters knows that in the middle of the day, you usually work kind of 800 or 1,000 or 1,200 mile distances during the day on 20 meters, and the coast-to-coast propagation is mostly not there. And the reason is, on 20 meters in the middle of the day in the summer, the E region is heavily ionized and our signals don't get through it. So how do we combat that? Well, we operate at higher frequencies during the day, especially in the summer, avoiding 20 meters so that our signals don't bounce off the E region. So we operate over above what's called the maximum usable frequency, and our signals propagate right through the E region, right through the F1 region, and go to this really high part of the ionosphere that gives us really strong signals all around the world. So at this part of the solar cycle, in the middle of the day on 20 meters, usually we'll operate on 15 meters or 17, or if we're really lucky, on 12 meters. For complicated reasons, usually 10 meters is not a very good DX band in the middle of the summer. I'll talk about that a little bit later. But 20 meters at night, 17 meters to 24 hours a day, and 15 meters almost 24 hours a day are really incredible at this part of the sunspot cycle where we are right now. Okay, I wanted to go there. I think I've already talked about what I wanted to talk about here. That phenomena is known as blanketing, E region blanketing of the higher areas in the ionosphere. Typically, this blanketing phenomena occurs from about 9 to 10 a.m. in the morning until mid-afternoon, when most of the signals you'll hear on 20 meters are from our other stations in the United States. If you're in the US, most of the stations you'll hear on 20 meters in the middle of the day will be from the US at distance of 800 to 1,200 miles. And then by the middle of the afternoon, the E region MUF drops below 20 meters, and suddenly propagation over long distances is good. So if we want to work de-expeditions in the Middle East, for example, and we want to work them on 20 meters for a variety of reasons, we probably look at 20 meters late in the afternoon or all during the night, but not in the middle of the day. I'll just describe one experience that I had. I operated an IARU contest from Alex's QTH KH6YY on the coast of Hawaii. And it was quite a wonderful experience. I was a 20-meter operator, and about 9:30 in the morning, all the signals on 20 meters vanished. Well, Hawaii is in the middle of this huge ocean, and when we experience this blanketing phenomena in the 48 U.S. states, what we observe is that all we hear is other stations in the U.S. for the most part, maybe some from Canada. But in Hawaii, in the middle of the day, you hear nothing because there are no other islands up to 1,200 miles out. So you hear nothing at all in the middle of the day. 20 meters is just totally dead. And it's like flipping a switch. Once the MUF allows the E region to become a blanketing region out in Hawaii, the band just closes, absolutely closes down and stays closed down all during the day. And then suddenly the MUF of the E region will drop below 14 megahertz and 20 meters becomes wide open again, just like someone flipped a switch. So the way you experience that in Hawaii is dramatically different than the way you experience it in the US, where 20 becomes a domestic band, and in Hawaii, it becomes a totally dead band. I was talking to Alex about this, K6YY, and he said, you know, Frank, we tried to combat this, and we thought that if we put up a 20-meter antenna pointed to Europe, very, very low, and I think he tried that at about 20 or 25 feet, that we could combat this problem. And it was a reasonable idea. And he said, well, let's give it a try. So I flipped over to listen on that antenna. And you know that the European signals that were 20 dB over S9 30 minutes before, I could now copy them on that low antenna at about S3. And on the higher antennas, I couldn't hear them at all. But the problem with that is that other than the signals that were way over S9 an hour or less before this started, I had worked all those super strong signals, and I didn't have any interest in trying to struggle to work stations that were S3, and I knew darn well that over most of the world, those Europeans were working very, very strong signals, and there wasn't a chance in hell that they were going to work an S3 station in Hawaii in the middle of the day. So that was a really dramatic experience, and it was blanketing caused by the MUF of the E region exceeding the 14 megahertz. Okay, so this is a fascinating aspect of propagation, especially for operators for 6-meter DXers. I'm not going to be able to go into a great deal of detail about how this works. It's fascinating physics, but what I'll focus on in the limited time I have available is the result of these physics for 6-meter DXers, but also 10 and 12-meter DXers, even 15-meter DXers at the very bottom of solar minimum when the F2 region MUFs really drop down. So what happens here is quite remarkable. This illustration is centered on the geomagnetic equator. That's right over Brazil, about 800 or 1,000 kilometers south of the geographic equator. And what happens at the geomagnetic equator is electrons are rocketed up at high speeds, well up into the upper parts of the ionosphere, and eventually Earth's gravity finally pulls these electrons back down. And when they come back down, they follow the magnetic field lines and don't come down vertically from where they originally came from. They come down north and south of the geomagnetic equator and create these intensified areas in the ionosphere called ionization crests. So TEP involves propagation coursing the northern ionization crest, which is nominally over Venezuela for propagation north and south from the United States, and the southern ionization crest, which is nominally over Bolivia and the very far western end of Brazil. And the kind of propagation that we're interested in, and its signals are just amazingly strong when this happens. Many of you have probably experienced this if you operate on 6 meters or even 10 meters. The signal begins, this type of propagation doesn't extend any further north on most days than Cuba or Puerto Rico or Haiti. We couple into another hop of propagation, maybe another F2 hop to get into the 48 U.S. states. Some people on some days in southern Florida can get directly into TEP, but if we're in Illinois or Northern California or New England, we need another hop by some other propagation mode. But those hops are pretty common. So what happens is when we get into this TEP mode, the signal propagates up to the northern ionization crest, nominally over Venezuela. And then if the MUF is just a little bit below where we're operating, so let's say we're on 6 meters or on 50 megahertz, if the MUF here is at about 40 megahertz or so, the signal doesn't come all the way back down to the Earth. It comes down, it bends across the ionosphere and then encounters the southern ionization crest. And then the southern ionization crest then causes the signal to come back down. And this creates incredibly strong propagation between Central America, the Caribbean, and especially Buenos Aires, and the same general area around the very southern part of Brazil and Chile. And signals are just unbelievably strong. It avoids having a hop at the geomagnetic equator. The signal just passes right across the ionosphere and comes back down. So a normal ionospheric hop is about 2,500 miles from, let's say, north to south. But this TEP mode is more like about 4,000 miles without a hop in the middle. Oops. So, and signals are just unbelievably strong. I remember a particularly unusual event that occurred with me on 6 meters probably 7 or 8 years ago, near a solar minimum. And propagation was especially good that day into Buenos Aires. And signals were really strong. So I decided, well, I'll call CQ and see what happens. And this station called me, and he was just only about S7, and most of the signals coming from Argentina were way over S9 on 6 meters that day. And we made a short QSO, and I could tell that he was very excited about making this contact. And he sent me an email and a couple of photographs of his station. And it was a little 5-watt transceiver sitting on a table on just outside from his house, and he had a loop antenna just sitting right above the transceiver. So that was about as basic a station as you can get. It was sitting out on his patio, and you can imagine why he was so excited to make that contact. But propagation was such that day that he probably made some more contacts that day also. He was a good, solid, easy to copy S7. But some of the strongest signals from Buenos Aires that they were way over S9. Fascinating kind of propagation, and it's very common, especially during solar maximum, is called long path propagation. And this illustrates one of the most common long path propagation occurrences, mainly because the population centers are so densely populated with active hams. So this shows a long path from the northeastern United States and eastern Canada here, where the X is there. And that path crosses over the far eastern part of Brazil, skirts the edge of Antarctica, crosses over VK6, the western part of Australia, and then courses over Indonesia and the Philippines, and then ultimately winds up in Japan, where there are thousands of hams. It's amazing during solar maximum how often propagation is actually taking place in the opposite direction. You would expect this propagation to go from the eastern United States up over Canada and Alaska and then into Brazil, but instead it goes this way. But it can be remarkable. And just like, let me go back to this slide. Just like when TEP propagation crosses the equator, it can sometimes it's like a duct, and it avoids intermediate hops back down to the Earth. It seems like for long path propagation, very often when it crosses the equator, signals are much louder than you expect. And many hams experience this on 20 meters in the afternoon, for example, when the VK6s are very strong, and when the JAs and the Philippine stations are very strong in the late afternoon. This also happens on 40 meters. But during solar maximum, it occurs at all kinds of crazy times. I was on 10 meters the other day, looking for some of the D expeditions in the South African region, 5H1KB, and some of the others. And I was surprised at high noon in Maryland that I was copying not only 5H1KB, and he was working lots of Japanese stations, that I could also hear almost all of the Japanese stations that were calling him. And that was long path from Maryland, coursing over Africa and then back up to Japan. I can't ever recall hearing so many JAs at high noon on 10, but this is just the way solar maximum is, and we're right at the end of the solar maximum phase. So we talked about the NASA Marshall Space Flight Center forecasts of solar flux. They also produced this very important forecast. And this is a forecast of disturbances to the Earth's magnetic field. This is what causes a lot of the disturbed days when we might decide to turn the radio off because the propagation just isn't that good. And just like for the solar flux forecast, NASA produces 3 versions of this forecast. So this is the average AP index, which is an index of solar geomagnetic disturbance. So the black line shows where we've been through the middle of 2025. And then the colored lines show what the forecast might be. The most likely forecast, the so-called 50th percentile forecast, is in green. So what is this telling us? It's telling us, so here we are approaching the middle of 2026 right here. So this forecast is telling us that most likely the fairly frequent disturbed days that we're having at this part of the solar cycle are probably going to continue for about a year into the early part of 2027, and the disturbances will start to be less frequent. So we'll have more undisturbed days, but of course we also know that the solar flux index will be lower. So we'll have much less 10-meter propagation. The openings will be shorter, but we'll have a lot fewer days when we just want to turn the radio off because the disturbances are so bad. And this is a very pessimistic forecast. We're not going to experience this. This says that these disturbed days are going to continue for another 3 more years. Well, that's just not going to happen. Maybe even 4 more years. There's no evidence at all to indicate that this very pessimistic forecast is going to occur. This one is probably correct, but they always produce 3 versions. So let's take a look at a couple of things on the sun, but we're going to focus mostly on propagation. So how big are these active regions? Remember, the active regions are where groups of sunspots occur, and they're shown in black in this case. But it's also where coronal mass ejections originate from these active regions, and these can be huge. This shows this is one of the largest sunspots ever seen right here compared to the size of the Earth. It's really huge. but in terms of relative to the size of the sun, not so big. But compared to the size of the Earth, very substantial. So during the declining phase, which is just where we're beginning right now, coronal mass ejections, these CMEs originating from these active regions, are still causing fairly frequent, strong, and fairly long-lasting geomagnetic storms. We were supposed to get one of those today. Didn't happen. The other thing that happens is solar flares, which we haven't talked about yet. We'll get to it. But solar flares also originate in these regions, and they cause these daytime radio blackouts that we'll talk about in a little bit. This is a cartoon that shows the magnetic fields from these coronal holes. Remember, the coronal holes was that very dark region on that image of the sun. And the coronal holes have magnetic field lines that extend far, far out into the solar system. And what's important about that is that these open magnetic field lines allow highly charged particles to escape from the sun and to form what is called the solar wind. And during this part of the sunspot cycle, from solar maximum through the declining phase, we get to have a type of solar wind known as the fast solar wind that is particularly damaging for HF propagation. Good news is, in about 4 more years, we won't have very much of that at all. So we're in the period of the sunspot cycle where the effects of coronal holes, these open magnetic fields, are still quite intense, and they're going to continue for a few more years, but they will gradually become less common as these coronal holes begin to occur rarely at the sun's equator, and they drift up north to the polar regions where they don't affect the Earth hardly at all. So we have to put up with that nuisance for a little bit longer, maybe a couple more years. And this is these are actual illustrations of coronal holes. This is the one on the right is a particularly nasty one, where that coronal hole extended across almost the entire distance from the North Pole of the sun all the way to the South Pole. And these open magnetic field lines allowed a flow of a whole lot of highly charged particles from the sun all the way through interplanetary space, including the Earth. This is on the left is a particularly large coronal hole. This one is a mere 450,000 miles wide, and a piece of that was pointing towards the Earth back in April of last year. We had a period of repeating disturbances from coronal holes last year. I don't know how many of you remember that, but about once a month, from April right through August, as this coronal hole rotated around the sun rotates about every 27 days. Once a month, this disturbance would reappear. It happened every month for about a week, from April through August or September last year. Very unusual repetition month after month after month, but this was a huge coronal hole. I'll just mention a couple of things on this slide. Many of these coronal holes are not as strong, so they have a much less severe effect. But the high speed streams from some of these coronal holes have much more severe effect. And I'll show a couple of slides that show the statistics of how often they occur and in what part of the sunspot cycle. And this illustration is kind of an interesting one because it shows the open magnetic field lines from coronal holes where all this magnetized material escapes, and the closed magnetic fields. These are sunspots here, and these closed magnetic field lines do not extend all the way out into interplanetary space. They stay relatively close to the sun. I talked about that big coronal hole last year that really played havoc with HF propagation for about 4 months, 4 or 5 months. And the sun, just like the Earth is tilted 23.5 degrees. That's what causes our seasons. Well, it turns out the sun is also tilted. It's tilted about 7.5 degrees. Um, and this causes an interesting phenomenon, and that is there are periods of the year when the Earth's ionosphere is more susceptible to the effects of coronal holes and even CMEs. And that occurs during March and early April, and during September and early October, when the alignment of the Earth's magnetic field and the alignment of the sun's magnetic field is, from our point of view, exactly wrong. So that the charged particles that escape from the sun, either from coronal holes or CMEs, are oriented just wrong, I'll use that term, so that they can be captured by the magnetic field of the Earth. And that's what we were expecting this week. But it didn't happen. Apparently, what happened is the CME that left the sun last weekend was oriented such that it just missed the Earth. We were expecting that it was going to almost be a direct hit on the Earth, and it apparently just missed us. Thank God. Most of the CMEs miss the Earth. And many of those that do hit the Earth have a muted effect, and I'll discuss the reason for that in a moment. So this is an example of some of these huge explosions of material from the sun. This is just a size comparison of some of these explosions of material from the sun compared to the size of the Earth. They're truly massive. And the CMEs extend. This particular explosion went out into the regions well beyond the sun, to compare that to the size of the Earth. But then the sun's magnetic field brought the material right back again. Well, the sun's gravity and magnetic field pulled it right back. But CMEs escape the sun and extend all the way out through interplanetary space, as do the explosions of materials from coronal holes escape from the sun. So we're going to look at some statistics to see, well, why do we care about this stuff? So this is coronal mass ejections. CMEs tend to be fairly focused. Not all of them are, but many of them are. So thankfully, most of them miss the Earth. But some of them wind up being a direct hit. And those that are a direct hit have a huge effect. So this is a statistics that shows the number of fast CMEs. These are the ones that escape the sun's gravity. So this at solar maximum, which is this goes back one solar cycle. It doesn't show the current solar cycle's data, but it's still valid. So during solar maximum of the previous solar cycle 24, there were about half a dozen CMEs a day, but almost all of them missed the Earth. But when you have that so many CMEs, the likelihood is that some of them will hit the Earth. And when that happens is when we get some really disastrous effects on HF propagation, which I'll talk about in a bit. So be happy that CMEs, most of them missed the Earth, just like the one missed us yesterday and today. This is a complicated chart, but the story is pretty simple. So here we are, we're near solar maximum, so we'll focus on the bottom part of the chart. And this just shows the relative frequency of fast CMEs, which are the most severely disturbance causing radiation of particles and their magnetic fields to the Earth. And they're much more severe than these coronal holes that I showed you a photograph of. Well, it's near solar maximum. The CMEs are the dominant cause, of almost all geomagnetic storms during solar maximum, and including through the declining phase, which is where we are right now. And we're going to be in the declining phase for 2 or 3 more years. So you can see from this chart that almost all of these geomagnetic storms, the minor ones here, about 1,100 per year, and the moderate ones about 600 per year, and the strong ones, which are ones we really care about, 145 a year, and the severe ones that thankfully don't occur very often at this part of a relatively weak solar cycle, and I'll talk about that in a little bit. But notice it's the fast CMEs that have the dominant effect near solar maximum. So we're on our way in this declining phase of the solar cycle. We're on our way to solar minimum, probably in about 4 more years. And notice at solar minimum, it's just the opposite. Coronal hole effects are the dominant cause of geomagnetic storm, except for the most severe ones. But notice that the severe ones are much, much less frequent at solar minimum. At solar minimum, get about 38 severe geomagnetic storms in the course of a year, whereas at solar maximum, we get 3 times that many. And at solar minimum, it's still the fast CMEs that cause these, but there aren't very many of those CMEs. But for the weaker ones, which are the predominant ones, so out of the there's like 25 times more minor geomagnetic storms at solar minimum than there are severe ones, and they're almost all caused by coronal hole effects and not by fast CMEs. We'll just take a couple of looks of some other statistics. From the point of view of solar flares cause what are called radio blackouts. And any of you who have ever experienced a really strong solar flare, you turn the radio on during one of these events, and it seems like the radio is broken. You don't hear anything, and maybe if you hear any signals at all on the HF bands, it might be someone on the other side of your town or someone in the next town over, where they don't rely on the ionosphere to propagate to you. But apart from that, you won't hear anybody on the HF bands from 40 meters all the way up to 10 meters. And this is an example of one of the most severe cases ever recorded in the modern era of HF radio, November 2003, when there are 4 of these very strong X-class flares. And I don't remember what HF propagation was like back then, 20 years ago, but I'm sure it was just awful. We probably didn't even turn the radio on for those 3 days. So what's actually happening here? The solar flares cause very intense X-ray radiation, and that X-ray radiation ionizes the D region of the ionosphere. That's that very low region of the ionosphere, and its only function from an HF radio point of view is to cause absorption. So the solar flare really activates the D region and causes absorption all the way up to the 10-meter band. It doesn't affect 6 meters to any meaningful degree, but it does affect the propagation all the way up to 10 meters. And one of the many interesting aspects of these radio blackouts is that the very strongest X-class flares can affect propagation on the 20-meter band for several hours, maybe even more than that. But the effects on the 10-meter band might last only for 20 or 30 minutes. And eventually the bands recover to just about as good as they were before the solar flare occurred. The blackouts are much shorter at the higher frequencies, like 10 meters, than they are on 40 meters, where they can last for many, many hours. So the strategy that you follow if you're, let's say, you're chasing a DXpedition or trying to work a friend of yours halfway around the world, is you know that these blackouts won't last forever. A minor one might last for only a few minutes, moderate one for maybe 10 or 20 minutes, but an extremely severe one for hours. So I already talked about the effects of CMEs. They're the dominant cause. By dominant, I mean like 99% of all moderate to severe HF propagation disturbances are caused by geomagnetic storms, and by far the most significant ones come from fast CMEs when the interplanetary magnetic field persists in the southward orientation. Let me explain that. Let's remember back to when we were in elementary school, and then we all experimented with bar magnets or horseshoe magnets. And we all learned back then that magnets had north poles and south poles. And if we placed those magnets on a tabletop and oriented them so that the north pole of one magnet was forced towards the north pole of the other magnet, that the magnets would oppose each other. They'd push each other apart. And then if you flip the horseshoe magnet or the barn magnet so the north of one side was oriented to the south of the other, they would pull together with significant force. Well, exactly the same thing happens in the outer atmosphere of the Earth. When a fast CME hits the Earth, if the magnetic field in the solar wind is oriented the same orientation as the Earth's magnetic field, most of these magnetized particles get pushed away from the Earth and have a relatively minor effect. On the other hand, about half of the time, these fast CMEs, when they hit the Earth, thankfully it doesn't happen that often, if the orientation of the interplanetary magnetic field is opposite from the Earth's magnetic field orientation, then the Earth actually sucks these particles into the Earth's atmosphere, kind of like creates a crack in the Earth's atmosphere and greatly magnifies the effects of the CMEs. So when the really bad CME effects occur when the interplanetary magnetic field from the sun is oriented opposite from the magnetic field of the Earth. And I think I've already talked about all this. So the most severe CMEs are really, really fast, 500 kilometers per second. Could that be true? Yeah, that's correct. The particles, the molecules that are highly ionized molecules that are expelled from the sun are very, very tiny. They have very little mass. So they can be accelerated to these incredible speeds, supersonic speeds, without any big problem. And that's correct. The fast CMEs that have the most severe effect are at 500 kilometers per second or more. It can be twice or three times that. So I think I've already talked about how often these CMEs occur. Yeah, so we've already talked about all of that. So let's talk about, again, the orientation of the interplanetary magnetic field. This just shows a cartoon. This line labeled BX is the orientation of the sun's magnetic field intersecting the Earth. And what we really care about is this line labeled BZ. That's the orientation of the Earth's magnetic field. So And what we really care about is orientation called minus BZ, which means that those are the occasions where the magnetic field from the sun, called the interplanetary magnetic field, is oriented opposite from the Earth's magnetic field. And the condition is referred to as minus BZ. And this little chart at the bottom, the severity of geomagnetic effects is measured by the KP index or by the AP index. They both measure the same thing. And if this is a BZ orientation of the interplanetary magnetic field lasts for a very long period of time, oriented opposite from the Earth's magnetic field, the effects are greatly exaggerated. So not only does the strength of the interplanetary magnetic field, but also the orientation greatly affects how severe the storm is. And the strong and severe ones that we really care about always occur when the orientation is negative, always. And it's very, very difficult, and maybe it's just about impossible, to forecast which way the interplanetary magnetic field will be oriented when a CME hits the Earth. So sometimes a very strong CME will hit the Earth, but it'll be oriented magnetically the same as the Earth's magnetic field, and the effects will be pretty minor. But on the other hand, a not so strong CME could hit the Earth, but with its magnetic field oriented opposite from the Earth, and its effect can be greatly magnified. Very hard to forecast. And just some more statistics. Thankfully, the really strong disturbances are K indices of 7, 8, and 9. And the really strong ones, the KP of 9, it's typically about 4 days or less per solar cycle. They're very uncommon, but their effects can last a couple of days. K index of 8 is more common. There's about 60 days per solar cycle where we get the K index of 8. And K index of 7 is more common, and 6 and so on is still more common than that. KP of 5 equates to a minor geomagnetic storm, and they're pretty common, about 900 days per solar cycle. But their effects last only for a few hours. So if a minor geomagnetic storm is ongoing or is forecast, you know that a few hours later, chances are most of the effects will be gone. And near solar maximum, the solar flux index is so high that it washes out the negative effects of these minor geomagnetic storms. So we get lots of minor geomagnetic storms at solar max, but we've got such a high solar flux index that the effects are almost inconsequential. And just more statistics showing how many days per year these extreme and severe storms occur. They're shown up here. And cycle 23, which was 22 years ago, was a much more intense solar cycle than this one, and the one solar cycle 24 that had solar maximum in 2015. And just another way to look at the statistics, this is for any particular day. So without any knowledge whatsoever as to what the geomagnetic disturbance forecast might be for tomorrow, you'll know that the chances are that the K index is going to be probably 2 or 3, something like that, is the most likely. And if there is a disturbance tomorrow without any knowledge of the forecast, chances are the disturbance is going to be minor. Pretty low probabilities of the more severe disturbances. And the minor ones, we can work around them. They don't last very long. And the severe ones, well, they're very uncommon. So maybe we find something else to do rather than be DXers on those very rare days. Yet another way to look at this, and this is amazing how our forefathers who selected the dates for the ARRL and CQ Worldwide DX contests, how they picked days of the year when the effects of these geomagnetic storms can be pretty severe. I remember when I was a very young ham, I operated in the ARRL sweepstakes in November 1960 when we had one of these very severe geomagnetic storms. And boy, I'll tell you, the bands were just about shut down at night. And the effects of geomagnetic storms are much worse at night. And I just turned the radio off, and then the next day it was better. So the chances of these happening are greater. And by setting the DX contest at the end of October and November, the effects are somewhat muted. And by setting the DX contests in February and early March, the effects are somewhat muted compared to the worst days. Another complex graph, and what this shows is the seasonal effects. The orientation of the Earth with respect to the sun's magnetic field. Remember, the Earth is tilted and the sun is also tilted. The sun's rotation is tilted 7 degrees. It causes geomagnetic storms and other disturbances to occur more frequently in late March and early April. That's what is shown here by the red. And for them to be very, very uncommon, especially here in December and January, but also in June and the early part of July. Later this month and in early July, you'll notice that the K index tends to be about 1 point lower than normal. You can see this. It shows right here that there's a variability between the most intense disturbed days in April and October compared to the most quiet ones, and the variability is from about the mid 3 level down to about 2. So there's about a 1 point variability of the K index between October and January. So January is a great time for low band DXing because the absorption is a lot less. The disturbances are a lot less. And the summer, not so much because the disturbances are more uncommon. There's another subtle aspect to this chart, and it's somewhat less important, and that is that there's also a variability of these disturbances versus time of day. And notice it's in universal time or Greenwich Mean Time, and that has to do with as the Earth rotates on its axis every 24 hours, there's a relatively minor variability between the sun's magnetic field and the Earth's magnetic field, and that's what causes generally somewhat quieter conditions to occur around the post-midnight hours, after midnight UTC, extending up until East Coast sunrise. So that's kind of an interesting phenomenon. And kind of unexpected too, but it's true, and it varies with universal time, not local time. And more statistics. This just shows the seasonal likelihood of geomagnetic storms, and you can see how they're about twice as frequent during the equinoxes as they are during the solstices. So we're in the summer solstice period right now, when the geomagnetic storms are about half as common. When really strong geomagnetic storms occur, the aurora can get pushed down over the northern part of the United States. And this is when we might want to get on 6 meters, but it really kind of wipes out our HFDXing ambitions. And this shows the southern extent of the aurora for various K indices. When the K index is 9, it can push the aurora all the way down over the central United States. Very, very rare occurrence and very hard to see, because in order to see the aurora over the United States, you have to have not only very high K index, you have to have the sky not lit by the moon. So it has to be in the 12-hour period when the moon is on the other side of the Earth, and it has to be on a day when there are no clouds. And ideally not in the summer when the nights are very short. So it's really hard to experience these in the US, in the mainland. Much easier to observe them up in Fairbanks, Alaska, or Iceland, where these are kind of very common events. One more aspect of the aurora, and that is it is centered not on the magnetic pole. You can see the aurora actually sits over the current location of the magnetic pole, which is just off the coast of Siberia. And instead is centered around the geomagnetic pole. What does that mean? The geomagnetic pole is the place where the magnetic field of the Earth extends out into space through the ionosphere. And that is still located in northern Canada, between northern Canada and the coast of Greenland, and it has hardly moved at all. And when you read these newspaper accounts of the movement of the magnetic pole, that does not apply to radio propagation. The geomagnetic pole has hardly moved at all, just 20 or 30 miles, whereas the magnetic pole, which is used for navigation, not so much anymore with GPS, but if you have a compass, the compass points at the magnetic pole, not the geomagnetic pole, and it has moved 1,000 miles over the course of the last 50 years. But the geomagnetic pole has hardly moved at all. So we don't, as DXers, we don't care about where the magnetic pole is. We care about the geomagnetic pole, which is still up over far northern Canada. So a couple of aspects of the auroral oval, and I've only shown one illustration here. This illustration is shown for noon in North America and midnight over Siberia. And notice some interesting aspects of the auroral oval here, and that it is relatively thin on the noon side, and it is relatively wide on the night side. And it is also pushed to lower latitudes after sunset. So the effects of very disturbed conditions in the auroral and the absorption in the auroral oval is primarily a nighttime effect. Just like on 6 meters, for example, trying to work auroral communications tends to be mostly, not entirely, but mostly a nighttime effect. Also, the disturbances caused by the aurora to HF tends to be mostly a nighttime effect. The daytime, much less. And I'm not going to read this slide because it basically says the same thing. The absorption that occurs on the HF bands in the aurora during these badly disturbed days is still the D region. That's the absorbing area of the ionosphere, and the disturbed aurora causes a drastic increase in the ionization of the D region, and that's what causes our problems in HF when the aurora is pushed to lower latitudes. Okay, this shows the frequency of M-class and X-class flares, and you can see how, you can see how they're pretty much correlated with the solar cycle. So this is solar max for cycle 23. This is solar max for cycle 24. So as we drift down towards solar minimum, these flares will become very uncommon. So we're about halfway down. So solar flares are still happening, but less frequently than they were a year or two ago. If anyone tells you they experienced a radio blackout during the night, don't believe them. These radio blackouts are caused by X-ray radiation from the sun and that's electromagnetic radiation. And when the Earth is in darkness, so when we're facing away from the sun, we're not exposed to this X-ray radiation. So the effects of solar flares are strictly nighttime effects, never daytime. But keep in mind that if we're trying to propagate across the daytime part of the Earth, so let's say the sun has just come up here in the eastern part of the United States, and we're trying to propagate to our east. Well, we'll be propagating during the day through the day part where the solar flares have a big effect. But if we're trying to propagate to the west, to Japan or Hawaii, that whole part of the Earth is in darkness, and solar flares have no effect. So it's strictly a daytime phenomenon, but it also depends on which way we're pointing our antennas. I think I've talked quite a bit about the strongest solar flares. The strong ones are the X class. They're pretty uncommon. This shows how often they occur. The X10 class are the really strong ones, and they're only about 8 days per solar cycle. We may not have any X10 class flares during this cycle. It's a weaker one, but we've had plenty of the weaker one, the X class. The M class flares, you'll hear about those. They occur much more often, about 300 days during the solar cycle, but their effects last only for 10 or 20 minutes, and then things return to normal. So this is just a summary of a lot of things I've already said. The solar maximum began in December of 2022, and we're just about the end of the solar maximum phase. In terms of propagation, the almost daily 10-meter propagation, we had January this year was really, really good on 10 meters. It was quite remarkable, but the propagation on 10 meters became a little bit less frequent, but 10 meters has been pretty good. But now we've gotten into the seasonal decline, and don't confuse that with the solar cycle. The seasons affect 10-meter propagation a lot, and the band is just not as good in the summer. We should expect 15-meter propagation to frequently occur right through about a year from now. But as we enter the summer of 2027, 15-meter worldwide propagation will be less reliable, but it'll still be useful. But we have to be on the 15-meter band at the right time. Where we are now in the declining part of the solar cycle, 15 is still quite a reliable DX band, as is the 17-meter band. The 20-meter DX band is a wonderful nighttime band at this part of the solar cycle, and that's probably going to continue for another year or two when 20 stays open all night long. By the way, the 17-meter band also tends to stay open for most of the night at this time of year. Turn your radio on 17 meters and you may be surprised. 40-meter propagation tends to last all through the night until we get to solar minimum when it becomes less reliable. So what bands do we want to use? Well, 10 and 15 meters provide really good worldwide propagation from September to April. And for the next year, we'll still be able to enjoy that, but not every day. But fairly frequently, and it won't last all day like it did during solar maximum a year or two ago, but still fairly reliable during some part of most days for about another year. And then we'll be starting to get much less reliable after next year, especially on 10 meters, a little bit less on 20. The nighttime, all-night propagation on 20 meters will last for several more years. 20 meters has always been the most reliable DX band. The only exception to that being during the middle of the day in the summer when it gets blanketed by the E region. And 40 meters is also a fantastic DX band during the night, as is 30 meters. The digital modes have really
I've been talking for 1 hour and a half.
Okay.
He's just finishing.
I'm just coming to the end. So I think I've covered these topics about the declining phase of the solar cycle. So I'm going to skip over these. This covers each of the individual bands, and you can read those on your own. Yeah, these are quite readable, so you can read those on your own. This goes all the way to 160 meters. I feel sorry for any 160-meter DXers. It's going to be probably 2 more years before that band starts to get a little bit better. And it won't get really better until we get to solar minimum in about the year 2029, 2030. So I'm going to close out the presentation with a discussion of what I refer to as nowcasting. Here in the 21st century, we have amazing tools available to us for free on the internet. This shows some displays that are available on a website called the Reverse Beacon Network. The website is shown at the bottom of the slide. And this shows CWCQs that were heard in North America at 0500 Zulu on 80 meters. And this happened to be in December when 80 is a pretty good DX band. So you can see all of these CWQSOs that were, these are actually CQs that were copied by receivers on the Reverse Beacon Network. And this is a very easy site to use. You can't break it, so experiment with it. You can select as many different handbands as you want, but this chart gets really densely crowded if you select too many bands. So it's usually best to select 1 or 2 bands. I usually select CW, and you can select individual call signs if you want, or any call sign. You can select a DXCC country or a zone or a continent, and it's really interesting to watch what's happening right now. So these are not forecasts. This is actual propagation happening right now. Why I refer to it as nowcasting. Very easy to use, free, reliable. But this is my favorite one, and this is my last slide. This is PSK Reporter. And even for hams who don't particularly enjoy digital DXing, this is still a wonderful tool for understanding what propagation is doing right now. So even if you're a CWDXer, it's used to getting familiar with this tool because it will show you right now what's happening with propagation. And this particular slide happened to be on 20 meters. It was taken at 2200 Zulu, and it showed the FT8 activity that took place between, that took everything that was detected at that time. So it shows lots of propagation between North America and Europe, especially Western Europe, fair amount into South America, a little bit to Alaska. And then, this is no surprise for us. Familiar with 20 meters, it's exactly what you'd expect. One of my favorite ways to use this website, since I'm active on digital, is I'll just get on the FT8 digital and either call someone and initiate a QSO or call CQ. And the receivers that feed data into this website will detect my activity all over the world and tell me where my signal is being heard. Both this website for digital signals, mostly FT8 and FT4, and the Reverse Beacon Network on the previous slide are really excellent for calling CQ and figuring out where your signal is being heard. And it's amazing how low you can turn your power level down, and some of these receivers will still hear you. Of course, your coverage will be reduced, and you can see where you're being heard, where you're not pointing your antenna either. So that's the end of my presentation. I'm sure I went over. Sorry about that. For those interested in asking questions about this, you could always send me an email at my email address shown here. And if anybody has any questions, I'd be happy to try to address those.
Well, Frank, on behalf of the club, thanks again for a really great, thorough program. And, we'll have this presentation up on our YouTube channel so that you can go through it, stop, listen. And we'll also have for our club members a summary that comes from the transcription of tonight's recording. So do we have any questions for Frank?
I think I wore everybody out. But can you imagine if we tried to enjoy our DXing hobby or our contesting hobby on the internet where everybody had the same propagation every day, all day? It would be nowhere near as much fun as all of this variability that we experience and the strategies we have to use in order to maximize our success despite all of the things that the sun throws in our face.
Absolutely.
Frank, I've got a question from another presentation you gave.
Yeah, that's okay.
You talked about using a dummy load to test coax. And I tested my coax I use on HF, and I started seeing the SWR doing some dips when I got above 100 megahertz.
Yeah.
Should I be concerned at testing at that frequency? It's HF. I use it for HF.
Yeah, and that was probably a flexible coax, I suspect, right? Like maybe
Yes.
213. Yeah. So you're just seeing irregularities in the coax. Um, if instead you were trying to run that same test on hardline, let's say Andrew LDF4 or even cable TV line, you wouldn't see as much irregularity. But with flexible lines, you'll see that. And you can even you can see the effect of bending flexible lines too tightly because it'll create a bump.
So I shouldn't be concerned.
No, but you can tell why serious VHF UHF DXers don't use flexible coax lines.
Okay, thanks.
Okay, yeah, but don't be worried about the effects on HF. They're minor. But if you have a piece of coax that's been deteriorated by the entry of water into the cable, you can really see that with the same test that you just ran. And what you're going to see is those irregularities all the way down into the HF range, and if you've got significant amount of water that's been in that coax for a while, the effects are pretty dramatic down in the HF range.
Gotcha. Thank you.
But if things are good, that trace is going to be nice and regular and flat across the HF range, and that's all you really care about if you're an HF guy.
Yes. Thank you.
Okay.
Any further questions for Frank? Thanks an awful lot again, Frank. And there's just a lot of good stuff that we can go back and look at and reflect on as we start this slippery slope down the other side of the solar cycle. So
Yep. Yeah, so the kind of the bottom line is we're still going to get quite a few of these disturbances over the next 12 to 18 months, but then they'll start to become less and less common. But solar flux index will be lower and lower and lower too, so it will become 40 and 20 meter DXers and not 10 and 12 meter DXers in a couple of years.
all right, well, everyone go out and enjoy the DX before it gets cold.
Yep.
6 meters is open.
To where?
It's a double hop from the East Coast to the Delta Norways and Delta Mikes.
Yeah, that's great.
West Coast.
And at this time of year, this is the time of year when we get the openings to Japan also. Those are amazing.
It's tough from the East Coast.
Tough, but not impossible. I've worked hundreds of Japanese stations on 6 meters. Hundreds at this time of year.
Right.
This is the ideal time of year from about the 1st of June until about the 20th or so, and it becomes less common after that. It's amazing. Who would have thunk that you could work halfway around the world on 6 meter sporadic E? but it's there and it's fun.
I'm listening with an 8 element beam, so very hopeful.
How high is it?
About 50 feet, 45,
Absolute,
47.
absolute ideal height.
Yeah, I mean, I based it on what you said.
Yeah, it's absolutely. Well, that's good to hear that at least one person listens to me. But you've done well. It's a fantastic antenna, and I'm sure you're having a great time with it.
It's a lot of fun, yes.
Yep. You never know what's going to happen. If you think HF is unpredictable, you ain't seen nothing yet until you get on 6 meters and work long distance sporadic E. It is absolutely unbelievable.
Keeps you busy.
What's the longest distance you've worked on 6 meters? Sporadic E.
Australia.
Yeah, yeah, good. I've worked that several times from the East Coast. My most distant QSO was with 3B9. He was pretty active on 6 meters last year and the year before, and that's one hell of a long way from the East Coast. And his signal was good. I've also worked into Kazakhstan, right on the Chinese border. That's
a good one
way too.
for sure.
Yeah, it's a lot of fun, and I understand that there's a station in Echo United, Belarus, in fact, there are 4 stations that have become active on 6 meters this season. So there'll be a lot of 6 meter DXers trying to work the Echo United stations this month. It's already been quite a few QSOs.
I'll be looking for them.
Yeah, I'm sure you will. Good luck.
Thank you.
All right. Good night, everyone.
Good night.